You heard that my name is Volker Blum of the Mechanical Engineering and Materials Science Department. And the thing I'd like to talk about today is our work on predictive simulations of materials for electronic and energy-related applications based on quantum mechanics. So our mission is to create simulation tools, at least that's a big part of our mission, for materials properties based only on the first principles of quantum mechanics. Trying to predict those, and one important aspect that this work is grounded on is actually the development of a large code package, which has numerous development centers in the meantime, that I'll speak about in the first part of the talk a little bit to say what this is. And this we apply, as Richard said, and actually with help from the Energy Initiative, to materials for electronic applications and also in an energy-related context. So the outline of the talk is basically this. I'll speak about the approach at first. I'll then come to the materials that we look at. And then towards the end of the talk, I'll say a few words about our efforts to try to bridge between basic academic research in this area and people in industry who actually need these theories to be accessible for them to do their work. And we've recently teamed up with a company called Quantum Wise in Denmark. That's a small company who are specialists in this, and we're very excited to see that happening going forward. So my background, as you already heard, is that I came to Duke about 1.5 years ago as an associate professor. Before that, for about 9 years, I was in Berlin at the Max Planck Institute, the Fritz-Haber Institute, where a lot of the basic work towards the methods development especially happened in this fine building up here on the first floor. The building that I'm in now is pretty much as nice as Hudson Hall on campus that you all know. And just to say who actually does the work that I'm speaking about, the group has grown to 7 people in the meantime and is going strong in all sorts of areas, and some of which you'll hear about in a moment. Now, the real introduction to the talk is that if we had a theory that could predict the right materials and molecules for a given task, in many cases, this is what might be missing to make a piece of technology do what we want it to do for us on a level that's cost competitive. Now, if we had that, we could hopefully dramatically accelerate the rate at which useful materials and molecules are found. And this is an idea that many people in the field propagate. In fact, this was embodied in the Materials Genome Initiative that you might have heard by the White House a few years back. And you can see from this title page of their PDF that you can download from the White House website still, I believe, where this applies. This goes from traditional engineering materials such as sheet metal here, I suppose, to electronic materials, all the way to renewable energy materials that David talked about just a few seconds ago. So this is what we'd like to do, and it turns out that happily we have such a theory in principle. So this is the Schrödinger equation, or Dirac's equation. I won't go into the details of what all these letters mean. This is a very short form. The key point is that this here is a mathematical operator that we know exactly, and this E here is an energy that's often the outcome for what we want from a mathematical point of view. And it was actually Dirac, not Schrödinger, whose equation describes everything we want to know from a chemical perspective. And Dirac himself noticed this in a famous quote in the introduction of an article he wrote in 1929, which said that the underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known. And then he goes on to say that it's unfortunately a little bit computationally complex, and therefore it becomes desirable that approximate practical methods of applying quantum mechanics should be developed, which can lead to an explanation of the main features of complex atomic systems without too much computation. And I've read this segment numerous times in my life, and maybe some of you have read this segment before too, but every time I read it, I'm actually impressed about how precise and visionary the statement was, because it's actually exactly correct, and that's exactly what a large field of people is trying to do to this very day, and this is actually becoming practical these days. Now, there are a few obstacles on the road. You can also call them opportunities. One of them is that material space is huge. So here we have the periodic table of elements, from very light elements to very heavy elements. If you count what you can make from this, of course, there's the whole space of molecules, which I won't even begin to count. You can ask mathematicians for libraries of molecules up to such and such many atoms, and those are billions. But if you look at inorganic crystal structures and just well-defined crystal structures, The latest edition of the Inorganic Crystallographic Structure Database lists 177,343 known crystalline compounds, and that doesn't actually include their defects or the complexity of combining them with other materials and trying to use them in practice. So this is good. We could try to predict the properties of this, but it turns out that in many cases the practical properties that are of interest are actually just at the limits of what theory can reliably do, or a bit beyond the limit. So this is a field that is indeed emerging as relevant for industrial applications, especially in the electronics and semiconductor industry. I think they do these kind of simulations. But it very much intersects with basic science because it's often the most esoteric kind of many-body theory that will give you the quantity that determines how the electrons flow through your semiconductor device. And that's why this is what highlights the importance of having fundamental academic research out there to push these methods forward at the same time as trying to bring them to a practical application. And to a large extent, that means we need to develop the theory, which has been going on for a long time, and the computational tools, and appropriate user interfaces all at once. So I wrote appropriate here, not necessarily simple or easy to use. Easy to use is always good. But appropriate in the sense that it turns out that people who use these user interfaces in an industrial context are actually experts of their own. They're not detached from an academic world, but they need to use them effectively to get the work done. I think that's really the challenge of the appropriate user interface. So I'll come to that towards the end of my talk very briefly. So in 2004, when I moved to Berlin, in fact that was the reason for me to move to Berlin from the US at the time, we began a new electronic structure code, which is a computer software that basically takes the principles of quantum mechanics and tries to predict stuff. And since this is a general theory, if you make a set of objectives for such a code, the first objectives that would be a nice to have, in fact that was our primary objective, was to be able to cover the full space of materials and chemistry in practice, not just in principle, but with the implementation that we wanted. Now, this means, first of all, to be able to cover what I call here materials and molecules. In technical terms, this means that you might want to be able to model a molecule in the vast infiniteness of some theoretical universe, but you might also want to model a periodic model of your material that's infinitely extended so that you capture the essence of a material in its practical environment, and then things in between. We did want to have the hierarchy of methods that's been developed in the field to this date. I won't say much about the details of these methods, but one thing I want to mention is that something called density functional theory is actually the main workhorse of this field that made these things practical. And for materials in particular, I think certainly since the early 80s that these calculations have become practical for increasingly larger models of materials. And then there's also stuff that I call here beyond, which is really the ongoing theoretical development, and you don't need to know all these abbreviations here, although I'll be happy to explain them. But these are different variants of something that's known as quantum mechanical perturbation theory. Interestingly, this is the first thing that Schrödinger, I think, suggested as a use for his theory, and this is the perturbation theory aspect is still going on today. We wanted a method that made no approximations at the outset. So in chemistry and materials, this means you want to treat the electrons, core electrons, valence electrons, in principle on equal footing if you can afford it. And we wanted something that was scalable in practice, not just with respect to system sizes that you can treat, but also computationally. So if you have a laptop, this is nice. If you have a computer with several tens or 100,000 of CPU cores, which you can get access to these days, with reasonable effort, if you have a good case, then you want to use that thing efficiently as well. And that's where a lot of the work went in practice. So by efficient, I mean you're not efficient just by making things faster, by throwing away approximations. The hard part is to be efficient while not sacrificing accuracy, which means that if you have a model of thousands of atoms, which is the limit of what we can probably practically do today with these methods, then you want to be able to go back and converge numerical approximations that you might make along the way for the real materials model in question, if that's what you need to do. So very short, this is what we have. So this is a long list, but most of it I've already said. 10 years later, this is a simulation framework that we can actually use for practical simulations. It's an accurate, efficient quantum mechanics model for material. The mathematical discretization that we use underneath, this is called here numeric atom-centered basis functions, is really what set our tool apart from others. I think it made it useful seamlessly from light to heavy elements and in a variety of versatile ways. We do have the capability of modeling molecular as well as materials periodic structure models, so that was an important thing. We have density functional theory in some of its more current variants, in fact, that are also important. So this development is by no means finished. The many-body methods that I mentioned, it's a scalable system that has been demonstrated on a Blue Gene P machine by IBM a while back to work on 292,000 CPU cores. In practice, 292,000 CPU cores is something that's fairly expensive to get, so you don't have these all the time. But it means that if we have a system with thousands of CPU cores, we can run efficiently on that for practical problems. And we have all sorts of properties that we can calculate, of course. But more interestingly, perhaps, is that this project, from its beginnings in 2004, has grown into something that has over 50 contributors so far, has seen them. I think there's somewhere well over 100 licensing groups at this point, and most importantly, there's active development, not just in Berlin where this started, or Duke, where I am now, but in numerous other centers around the world, and we're also very excited about this collaboration with QuantumWise that I'll come to in the end. Just one thing about the scalability to show that this works for large systems, 5 minutes. I'll say very briefly that if you have a big problem like this, which is a problem with maybe 88,000 basis functions, 2,300 atoms is what I should really say. You see that on 320 CPU cores, the total time to compute this goes up fairly a lot for a single calculation, and you might want to do many of these. So if you use more CPU cores, you can bring that time down to this work. Now, what we calculate in practice on many things, it seems that the most relevant properties that we can make the most use of are actually conceptually fairly simple quantities. One of them is the total energy that turns out here. This essentially determines a question as simple as can a given material be made. I'll come to that with one example in a moment. There's all sorts of other quantities that relate directly to the total energy of a material, like elastic response, effect properties in the material, the thermodynamics, and so on. The second quantity, interestingly, is the so-called band structure, or the electronic levels in the material, which, if you haven't tried theoretical solid-state physics, is sometimes a relatively esoteric concept. It's lines that look like this. These are electronic energy levels, so here's an energy as a function of their momentum in a crystal. But this is really what you need if you want to do a device simulation in principle for a semiconductor material. So that's why this is interesting. We do have a variety of projects going on in the group that use that. I'll focus on one thing that I don't often talk about, which is something called, so far at least in this context, which is something called graphitic carbon nitride materials, which are interesting for their photocatalytic activity, actually. So if you want to do something like this here, shown very naively in this picture, take the sun, shine it on a glass of protons solvated in water somehow, and out comes a solar fuel, hydrogen. This is the prototype of a solar fuel that you might want to use to take solar energy and store it directly as a usable fuel. And there are many steps missing here. You need a photocatalyst that's somewhere to do this, a material. There are many materials around. You typically also need co-catalysts like platinum. But the challenge is that if you want to make this usable, you need something that's abundant in terms of elements, so you can do this at a large scale. The process to make the material should be cheap, and of course it should be active in the visible spectrum. And this is a thing that many people work on, but the ideal photocatalyst, I think, has not been identified yet to make this as viable as, say, photovoltaics. So one class of materials that we got involved in certainly has some of these characteristics, and this is carbon-nitrogen-based materials, which are made of obviously abundant elements. The synthesis process, this is a complex slide, but the key point is the synthesis process is relatively easy. You take a simple precursor molecule, heat for a while under certain conditions, you come to this molecule, you heat some more, and you come to this layered structure here. That's an actually active compound. This was realized about 6 years ago, and since then the activity on those materials has exploded. Now, one thing that I want to highlight in the context of this talk, just for brevity, is this material here, which is what a lot of the theoretical activity and synthesis activity is focused on. This ideally might be grown by heating a little bit more, but it turns out that if you look in detail, the experimental evidence for the existence of that particular material is not so great, yet there are a lot of publications on there. So Tiago Butari here in the group, and also Will Hoon, a postdoc, did a series of simple calculations based on the chemical reaction equilibria, and I'll just show you the outcome of that in terms of so-called temperature-pressure phase diagram, where the relevant pressure is actually that of ammonia, which is one of the products that comes out of the material if you want to condense it further and further to become this final graphitic carbon nitride material here. It turns out that you can find ammonia temperature and pressure ranges that are experimentally relevant, both for this single molecule as well as for the melon, which is photocatalytically active. But the range where you can make the hypothetical graphitic carbon nitride material is very, very small. So this is a logarithmic scale. So this is about 10 to the minus 8, 10 to the minus 9 below atmospheric pressure for ammonia. And then at very high temperatures, almost where these compounds become unstable as a whole in an experiment. So if you have a framework that gives you such a prediction, you can see relatively easily that perhaps a straightforward chemical synthesis route, which has been tried for 15 years or so for that layered material here, is not the way to go. It's actually relatively unlikely that this is the route to make it, and that, of course, also creates opportunities to make it later.
I didn't mean for that to be so abrupt. But
the peak is here. I will say very briefly what I wanted to say, but didn't get to in the context of this talk, which is how to transfer this to industry early. We are working with Quantum-wise, a company in Denmark, which is a very promising company to do that. We're actually filling a gap at the high end of the methodological spectrum that they have. And very briefly, we did have a joint development with them towards the user interface, and they're having their first household name industrial customer, I think now, after the paperwork on different sides there was finally done. And with that, I'll show you my summary. The key summary is really that I think these techniques will see sustained growth and continued adoption at the interface between relatively challenging academic research questions to get to the quantities we need, and industry applications in all sorts of areas, not just what I spoke about today. But thank you very much for your attention, and yeah, I'm happy to hear your questions.
questions for Volker?
So the software package, very interesting. I know you didn't have time to allude to the work, but I saw your high precision graphene films on the silicon carbide semiconductor. What sort of benefits did the software contribute to that work?
Right, so it was actually in that case a relatively similar case. So this is this material here that I didn't talk about much due to lack of time. This is a material that's also been made for 10-15 years now. It was made earlier, but at that time people didn't realize they were making graphene. The nice thing about graphene on silicon carbide is that you can make graphene directly on an insulating, so semiconducting material without having to transfer it there. Typically, if you use graphene for something, graphene is very well known and very much hyped these days, but you have to make the graphene somewhere, transfer it from a substrate, put it on the substrate that you actually want to use it for, and that might damage the material and doesn't give you the highest quality. Here you can make what the experimental people in the field refer as wafer scale graphene, simply because you can make it by evaporating silicon out of the silicon carbide, and that will leave the graphene over. Now what we could show with very similar calculations as I talked about was that there's actually a narrow range of equilibrium conditions where this material grows on its own. So if you heat to the right temperature and have the right silicon background pressure, ideally this material should form, and that's how it's made in experiment. Okay, that's good. We should have been there 10 years earlier, because experimental groups figured out the recipe on their own, although I doubt anybody was able to prove it's an equilibrium phase. But interestingly, people have also focused on the other side of this crystal. So what's subtly not apparent perhaps too much unless you know it, is that this crystal has two sides. One side where the silicon atoms are on top on one side, where the carbon atoms are on top of these bilayers here that form the crystal. If you try the same thing on the carbon face, and people have tried this for a long time, you don't get such nice films, although you get higher mobilities in the films that you do get. But it turns out that the single layer graphene films are actually not thermodynamically stable on that face because other phases get in their way. And that means that a straightforward manufacturing process that works on this face of the crystal will certainly not work on the other face of the crystal, so you need to find something different. That's something we can say with relative ease, I think, once we know what we're looking for.
Thank you.
Yes.
Can you talk a little bit about how you work with QuantumWise and what they're doing, how you're getting exposure to industry? QuantumWise, how you're working with them and how they're gaining exposure to industry?
So their mission really for a long time has been to utilize electronic structure-based methods for materials simulations at the atomic scale. I think that's their mission. That's directly from their mission statement. And their background, because the founder and many of their people come from electronic transport, their background is really, core market is really geared towards semiconductor modeling, although the modeling tools they make are general, I think. So the short description of the company is here, which is they operate worldwide. They're a relatively small business, and I think they handpick their employees actually from the community that makes these simulations in academia. And the customers that they have is a group of, I think, household names in electronics, materials research, and then a number of academic groups. I think not all their customers are public, but certainly these are fairly big companies that are interested in miniaturizing semiconductor technologies as much as possible. And there are 2 or 3, I think, out there that then feature. So that's what they try to do. In practice, you're not done if you can do quantum mechanical modeling, because you want to go to relatively large scales, even for what we can do. Even if you're at the scale of 10 nanometers or 20 nanometers, this is not done with just 1,000 atoms in your model. So what they try to do is cover a whole hierarchy of methods in their utilities. And this is here plotted as the number of atoms versus the applicability of the method. So for these high-end methods, they're rather general, like Schrödinger's equation, which you can essentially apply to any element, and if you do it right, you would get the right answer. You can't do that for 10 to the 6, 10 to the 7 atoms. There you need to have something that's very specific to your model, so you need to parameterize very well to get out what you hope to get out. And their existing tools, I think, cover this intermediate range of simulation techniques that would be needed to get to the device sizes that their customers are interested in very well. But if you want to go to the high-end, high-accuracy materials, where some of the interesting new materials are happening that you could use for applications that are simply not there yet, that's what they were lacking. And this was a natural fit, because that's exactly what we can cover with our methods. So our code is geared to the high-end, to relatively large structure sizes in this range here, but with an emphasis on keeping accuracy for the quantities that we calculate. That's how this fit.
All right, well, let's thank Volker.